start today's day. And again, we have two lectures, and the first of them will be given by Yana. But I want to give a short announcement just to recall that today we will have bigger lectures. So we will have lecture, short break, and then the second part of the same lecture. So just in case to be ready to have longer lecture now. Okay, so.
Okay, thank you. So yes, I recall you what was the original plan of this lecture course, and taking into account that we have 4 days instead of 5 days, I have decided to reconstruct it a little bit. So I have decided to shorten lecture 3. I have deleted a lot of material from this lecture 3, and only what is completely necessary for lectures 4 and 5 will survive. So this lecture 3 will be like half of a lecture today, then we will have a break, and then we will have lecture 4 today. And so, again, probably not the whole lecture 4, but just as much as we will be able to survive. Okay. And then tomorrow we will focus on lecture 5, probably. So my aim is probably to try to make more details, because I have realized that yesterday everything was quite fast and probably not that easy to follow. So I will try today to write down something, to clarify something. So let us try. Okay, so we start with lecture 3. So different approaches to construct and approximate operator semigroups will be discussed. And actually, the only thing which will be discussed in details is subordination in the sense of Bochner. Okay, but we will briefly make an overview of all other approaches. So the main question for the lecture 3 is how to construct or approximate or represent a semigroup, a strongly continuous semigroup. So natural questions which are related to this one. So if we have an evolution equation, that is, we have some operator L. So the first question, does this, precisely this given operator L, generate a strongly continuous semigroup? If yes, how to determine or to construct this semigroup? So if an explicit construction is not possible, so we don't know how this semigroup looks like, so how to approximate this semigroup, or how to represent this semigroup with some formula which still allows to calculate something. So there are several approaches how to approximate a semigroup, and in all cases we call that the semigroup, it is some object which in some sense, or strongly continuous semigroup, always has its generator. So in some sense, semigroup, it is something which replaces or defines the exponential function of its generator. So this is the true meaning of the semigroup. So the first approach is like follows. So if we have an operator L, the aim is to find a sequence of bounded operators L such that they converge to our given operator L, and such that, so if we have bounded operators L, they definitely define a semigroup, just by Taylor series formula. So if we succeed to construct such a sequence of bounded operators Ln, which approximate given operator L in such a way that the corresponding semigroups e to the power t Ln also converge somewhere, and their limit is not just something, but the limit possesses the properties of a semigroup, and more even strongly continuous semigroup, and we calculate its generator, and it turns out that generator is L, then we are done. So how to define e to the power tn for some L? Find bounded operators which approximate L, and yeah, so this is the approach. Okay, so this approach is realized in the famous Helios-Cedar theorem. This is the cornerstone of the whole theory, which says that so if we have a strongly continuous semigroup, then some properties are satisfied, and if these properties are satisfied, then there is an explicit construction which allows us to create the corresponding strongly continuous semigroup, exactly like this. So, hence, this Helios-Cedar theorem gives this if and only if condition for existence of a strongly continuous semigroup. But I'm not going to go further in details. It's a standard things which can be found in the books. So just the approach. One of the approaches how to define e to the power L for some given L. So this is one of the approaches. There are also Trotter-Carter theorems which give some other conditions when one can use this way to construct the semigroup. Okay, another approach is given by Chernoff approximation. So this is the object, so the subject of lecture number 4. We will discuss it in all details today, after the break. And roughly speaking, this is a very wide generalization of this nice formula, which I hope you all know from your first year at the university. So we approximate exponential function by this. So in Russia it is called first wonderful limit. I don't know how it is called in China, but first wonderful limit. Okay. There is also another approach based on the so-called perturbation techniques. It is, again, roughly speaking, a very wide generalization of representation of the exponential of the exponential function as a series.
For the third one,
yes.
This, in general, your L is unbounded. So
yes,
you may
yes,
have
yes.
some problems how
Of
to
course.
iterate.
Of course. We don't go. I just make a hint in how to say what kind of approaches, how they could be understood in principle, how many of them exist in the nature. Of course, if we start to discuss it, then one lecture for each, at least one lecture for each approach. That's why we will discuss only this approach. Okay. But still, everything can be found in the books. And these two things are purely standard things. But this is just for the orientation that such things exist in principle. Another technique is based on the following. When one proves the Helios-Cedar theorem, one realizes that so there is the so-called resolvent. If you know what is it, it's okay. If you don't know, just it's a small remark, don't worry. So it turns out that resolvent and semigroup are related by Laplace transform. That is, the resolvent is the Laplace transform of a semigroup. Hence, the natural idea would be just to invert the Laplace transform. That is, under some conditions, it is probably possible to invert it, and then semigroup is just the inverse Laplace transform of a resolvent. Resolvent, it is something which we construct from L, from the generator. So this gives rise to the theory of analytic semigroups, because to invert Laplace transform, we need to apply it to a semigroup which defines not only for t positive, but for some complex t as well. And there are a lot of books devoted to theory of analytic semigroups, but so in principle all this is based on this idea to somehow create something similar to inverse Laplace transform of a resolvent. Okay, fifth approach is as follows. So assume we have some simple, so to say, simple operator L, which does generate a semigroup, a strongly continuous semigroup, or even there is a Markov process behind it. Then one may construct new operator L star from L by applying some operations. And then hopefully this new operator again generates a new strongly continuous semigroup and also corresponds to a new Markov process. So there are many, not many, but there are several operations known on semigroups, and today we will discuss one, which is subordination in the sense of Bochner. Okay, so one more result which is important for quantum physics. It is about the case when instead of Banach space X, we consider just Hilbert space X. So if my L is a self-adjoint operator in Hilbert space, then e to the power imaginary unit Tn. So this guy is a unitary zero group, so strongly continuous even group. So my T is here not only non-negative but also negative. So this is defined by means of spectral calculus. So if we have self-adjoint operator, we have spectral theorem. So we can construct functional calculus considering different functions of L. So this guy is well defined, and it turns out that this is a unitary strongly continuous semigroup. And this is if and only if. So this is like a separate result, but important for quantum physics. And concerning the question how to represent semigroups, we know already that if my operator L is related to some Markov process, then we have this representation for the semigroup. This relation also can be generalized, but we will discuss it probably tomorrow. Okay, so now we will discuss approach 5, operations on the operator. Namely, we will discuss only one particular operation, which is interesting for us. This is the operation of subordination in the sense of Bochner. And we start with a family of measures, which I called yesterday convolution semigroup of measures. So yesterday we have discussed that we can consider families of measures on Rd, not on R1, but on Rd, which possesses the following properties. So the measure of the whole, each measure eta t of the whole space is small or equal to 1. That is, we deal with subprobability measures. They build the semigroup with respect to convolution operation, and so this family is continuous in some sense, which we do not clarify, but this means that eta t converges vaguely to delta, Dirac delta measure concentrated at 0. And I also said yesterday that if we have such a family of measures, it corresponds, so to say, 1-to-1 corresponds to some Levy process. So let me clarify this statement in more details. I'm not going to prove, but let me clarify what is meant at least. So for each such family for each such convolution semigroup of measures, we can create a Levy process such that the distribution of each random variable zeta t is exactly given by the measure eta t. And vice versa, for each Levy process, the corresponding family of its distribution build a convolution semigroup of measures. I'm sorry. So once again, what is a Levy process? So I consider the simplest case. So my zeta t is a Levy process without killing. So it's a more classical case without killing. Without killing, this means that the process does not die out. That is, it always lives in the state space. That is, the distributions of these random variables are always not subprobability measures, but probability measures. And by our definition, these are measures eta t. They are probability measures. So what is the definition of a Levy process without killing? So by default, each process starts at 0. So if So as I said yesterday, if we want to make a process which starts somewhere else, like in x, then I just consider x plus zeta t, where zeta starts at 0. Then this process will be again a Levy process which starts with, so the Markov process with the same transition kernel as this process, but starting at x. Okay, so I write down the definition of a Levy process. So it's a process which starts at 0. It has a stationary increment, it has independent increments, well, and it is stochastically continuous. I do not discuss what does mean stochastically continuous, but just this is something what is related to this notion. So these two notions, they correspond to each other, and that's all. But let me clarify how we obtain this property from these properties. So I will write down it here. So if we have stationary increments, this means that, for example, that zeta at time t minus s, probably I will write down just here, that zeta at time t minus s has the same distribution as zeta t minus zeta s. Here I can say this is zeta at time t minus s minus zeta 0, but zeta 0 is 0 almost surely. Yes, so I have shifted. So is it clear? So this. Yes. So Brownian motion is a particular case of Levy process. So you just do the same, what is known as Brownian motion. So independent increments from this form, in particular, 2 increments. So here I have chosen s smaller than t. In particular, here for 2 increments which are just coming from each other, one after another, like s smaller than u smaller than t. Then like zeta t minus zeta u is independent from zeta u minus zeta s. So let us use this to show that the corresponding property is satisfied. So how to show it? So consider. So let me write down here. So consider a random variable, the random variable. Let me call it x, and this would be just zeta t minus zeta u plus zeta u minus zeta s. This is of course zeta t minus zeta s. Then what do we have then? The distribution of this random variable. It is the random variable is the sum of 2 independent random variables. So the distribution of this random variable is just a convolution of these 2 distributions. Of distribution of zeta t minus zeta u convolved with distribution of zeta u minus zeta s. So this is the course of probability, first semester. Okay, now we use this property, that the distribution of this increment is the same as, so I will write down the above. So the distribution of this increment is the same as distribution of zeta at time t minus u. And the distribution of this increment is the same as distribution of zeta at time u minus s. Yeah? And this is nothing else but the distribution of this guy. So this is because of this identity. Yeah? This is the distribution of, again, this increment, but it is the same as the distribution of zeta at point time t minus s. Yeah, taking into account that we have this definition, we have just established this formula. Yeah, so if I call this like I go A and this is B, then this is A plus B. Okay? So this is just exactly what is written here. So at least if we have a Levy process, then the corresponding family of distributions is a convolution semi-group of measures. But vice versa, it is also so. Having semi-group of having convolution semi-group of measures, we can construct. Yeah, we're using Kolmogorov theorem about the existence of a process with given family, consistent family of interdimensional distributions, and then check that the process is exactly as we want. Okay, so it was all this was to persuade you that if we have a family, so if we have a convolution semi-group of measures, it corresponds to a Levy process. So it kind of one by one in the one-to-one correspondence. If I mean that I identify all Levy processes with the same distribution. Okay, now we consider a particular case. We live not in RD but only in R1. And I have an additional assumption that the support of my of the measures in this family, they all live in this half line. This means, so this additional condition, this means that the corresponding Levy process has non-decreasing paths. So let me clarify this. So why the process has non-decreasing paths? So if I have this property that support of my measure eta t belongs to this interval for any t, in particular also support of measure eta t minus s belongs to this interval for any t bigger than s. But this measure is the distribution of the random variable psi t minus s. But we have already discussed that this random variable has the same distribution as the increment psi t minus psi s. Yeah? But what does mean that measure, so distribution of some random variable lives here? This means that the random variable takes only non-negative values. Hence, this increment takes only non-negative values. That is, psi t not smaller than psi s. The paths are non-decreasing. So I'm drinking and you are thinking. So you agree? Okay, so let us assume that we have a convolution semi-group of measures on R1 such that their support lives in this half line. Then, so this convolution semi-group of measures is associated to a Levy process with non-decreasing paths. Such processes, one-dimensional processes with non-decreasing paths, which start at 0, they are called subordinators. Why they are called this way? Because we can consider such processes as random time. So naturally time grows, yeah, and it is not negative. So now we have something random, which also, okay, does not decrease at least, and yeah. So the idea is that subordinators, so such stochastic processes, can be used as a random time change. So we have new objects. Convolutional semigroup of measures on R, whose support lies in this half line. It corresponds to a process, a Levy process with non-decreasing paths. Such processes are called subordinators, and the idea of them that they can play the role of random time. Okay, further, for each convolution semigroup of measures on RD, without this additional condition, for any convolution semigroup of measures, I can assign, again, this would be one-to-one correspondence, I can assign a function which is called a Bernstein function in such a way. So we just consider Laplace transform of measures eta t. This is the definition of the Laplace transform, if you don't know what is it. And the statement is that if we have a convolution semigroup, then the Laplace transform of all measures eta t have this form. Here with some function f. And this function f is called a Bernstein function. So let me again persuade you that if we have a convolution semigroup, then its Laplace transform should have this form. That is, we have the same function f for all measures eta t, for all t's. But for that I have to do something. So, Laplace transform of a measure, of any measure, including a finite measure, in particular eta t, at some point z, is by definition integral from 0 to infinity e to the power minus za eta t dA. And this is well defined. So we know that eta t is a probability measure, or subprobability measure, but bounded measure. So this integral makes sense for any z, which is a complex number whose real part is not negative. Yeah. So consider z which is equal to is for some s real number. So it's okay. Yeah, it belongs to this allowed set. Then what do we have? Laplace transform of measure eta t at point is is integral from 0 to infinity e to the power minus isa eta t dA. And we know that eta is a measure which has support exactly here. So if I just, instead of 0 here, write down minus infinity, nothing will change. Yeah, because integral from minus infinity to 0 will be 0, because measure doesn't have support there. Okay, but then this is up to a constant, the Fourier transform of the measure eta t. So it is, okay, 2p 1/2 Fourier transform of measure eta t at point S. But this is already, so we have discussed yesterday that, so there is a function which is given by a Levy-Hinchen formula such that the Fourier transform of such convolution semigroups is given in this way. Let me say for some psi given by Levy-Hinching formula. This is that awful formula with constant coefficients which we have seen yesterday. By Levy-Hinching formula. So yesterday we had a big formula, I called the terrible formula. In the special case of this terrible formula has a constant coefficient, no dependence on x. It is the Levy-Hinching formula. So this we know. So actually if we take f such that f of is is equal to psi of s, then we obtain the statement what we need. That the Laplace transform has this form. Okay? So I have tried to persuade you that if I have a family of if I have a convolution semigroup of measures, then there exists a Bernstein function. So convolution semigroup of measures on R such that their support is here. Then there exists a Bernstein function such that the Laplace transform for each measure eta t has this form. So for the same f. So f is a kind of a modification of the psi which we have seen yesterday. Okay, so since for psi we have a Levy-Hinching formula, then we also have a kind of Levy-Hinching formula for f, but it looks a little bit simpler. In the sense that we should take into account that the support of the measure is here, and that is the corresponding process has non-decreasing paths. That's why the Levy-Hinching formula looks a little bit differently. That is, we still have a zero order term. We have a first order term. So it is instead of my c yesterday, my first order term has lambda here, which is also non-negative because my deterministic drift should be in the proper direction to have a non-decreasing paths. The second order term will vanish because if we have a diffusion, we cannot guarantee that the paths are non-decreasing. Yeah? Diffusion is always Brownian motion, has paths which are not monotone. And this is the general situation. So second order term is not here, and then the last summand. So it turns out that we need to require more for a measure. So yesterday it was a measure nu, but now we have measure mu, and a more restrictive requirement is needed for this measure. But this requirement implies in particular that so yesterday we have seen this terrible last summand integral, where we have three summands here in the brackets. So the last summand here is integrable if we have a measure with this condition. So we can integrate it, and then it will be just added here, roughly speaking. So it also disappears. So only first two summands survive in comparison with yesterday. And also again this measure mu, which was new yesterday, in a sense. It also explains us which jumps are possible and what is the intensity of these jumps. But if we want to make paths which are non-decreasing, only positive jumps are possible. That's why this measure lives not in R without zero, but only in this half line. So we integrate from 0 to plus infinity, not on R without 0. So this is also a difference with, in comparison with yesterday Levy-Hinching formula. So what I'm saying is just that this is also a Levy-Hinching formula. It looks a little bit differently in comparison with what we have seen for psi yesterday, but after some argumentation, one can check that they are related. Okay, so what I wanted to say is actually the following. Yes, an example will come soon. So as soon as we have a convolution semigroup of measures on R, such that their support is like this, then there is a one-to-one correspondence with the distribution of some Levy process with non-decreasing paths. There is a one-to-one correspondence with some Bernstein function, such that it is a Laplace exponent of these measures at a t. And there is a one-to-one correspondence with this triplet sigma lambda mu, where sigma and lambda are non-negative numbers, and mu is a measure satisfying some condition, such that I have this representation for this Bernstein function f. So as soon as I have this object, I have immediately four objects. This object, this object, this object, and this triplet. So this is the only thing which you have to remember actually for the future. Okay, and example, yes. So if we consider a function which is a power function for power between 0 and 1, then this is a Bernstein function. And the corresponding Levy process with non-decreasing paths is called beta-stable subordinator. Of course, I do not prove this, but again, you can find in the literature the particular choice of the measure mu, which leads to this function in this Levy-Kitchen formula. The particular choice of lambda, sigma, lambda, and mu, which provide us this function from this formula. It is not that difficult, but I keep as exercise. Okay. So now, it was just a preliminary. We have discussed this object. Now, what does mean subordination in the sense of Bochner? Now I have two objects. First object is a strongly continuous contraction semigroup on some Banach space. So as soon as we have strongly continuous semigroup, we can calculate its generator. So this is one object. And another object is a convolution semigroup of measures on R, such that the support of each measure lies in the half line. And again, as I said, as soon as we have this object, we have immediately all four objects. So this convolution semigroup of measures, the corresponding subordinator, Levy process with non-decreasing path, the corresponding Bernstein function, and its corresponding Levy characteristics. I'm sorry. So having these two objects, what I'm going to do. So I have this original semigroup. Now I want to make some operation on this semigroup to create a new semigroup. And I do it like this. So I consider the family of operators on the same Banach space X, where TT is defined. And my new family of operators is defined in this way. So how I apply this operator to an element phi. I take the original semigroup, apply it to phi, then I have some Banach space valued function of variable s, and I integrate it over s from 0 to infinity with the help of this measure at a t. So this t here is exactly as t here, and s will be integrated. So this guy is well defined because my t, my original semigroup is a contraction semigroup, so the norm is bounded. The norm of this guy is bounded by the norm of phi. So it's a bounded function of s, bounded Banach space value function of s, and eta is a bounded measure. So this integral is a Bochner integral, which is just a natural generalization of Lebesgue integral, so measure integral, is well defined. Okay. Moreover, it turns out that such family of operators is again a semigroup, even a contraction semigroup, even strongly continuous semigroup on this space, and hence we have succeeded to construct a new semigroup starting from original one.
So you basically you change the time and take
Yes,
the
yes, yes,
expectations
yes,
to the
yes, it will
subordinate.
come. It will come in a minute, yes. I am changing the time. But first, staying pure analytically, we just have this integration. Everything is well defined. If you calculate the norm of this operator, you will see that this is a gain 1, or small or equal to 1, better to say. So why it is a semi-group? It follows from this convolutional semi-group property of measures. Yeah. So yes, now what Professor Chen has already said. So this formula, so what do we have? We integrate this function of variable s with respect to measure eta t, which is just a distribution of random variable psi t. So this integral is nothing else but expectation, where instead of my time, we have this my new time, my random time. Yeah, so this subordinator is used as new time, and it is a random time. So this operation is just taking expectation of this guy. Okay? So is it clear here? Well, now if my semigroup, my original semigroup TT also corresponds to some Markov process, yeah, so if we have this representation for my semigroup, original semigroup TT, then I can insert this formula just here. So if I take this Markov process psi to be independent from the process zeta, which corresponds to the subordinator, then so first of all, if I insert this guy here in this formula, I obtain double integration. Yeah, so if two processes are independent, I just have Fubini theorem and double integration. We integrate with respect to distribution of this process, of this random variable, and we integrate with respect to this process. So, inserting this formula here, assuming that two processes are independent, we obtain this capacity presentation for this subordinate semigroup. It looks like this. That is, here we have psi, which is a Markov process which corresponds to the original semigroup, TT, time changed by subordinator, which corresponds to this eta. So you see? So there are two sides of this operation, analytical side of the operation. We take a semigroup, we take a convolution family, a semigroup of measures, we consider this integration, and we obtain a new semigroup. And now stochastic interpretation. We take a Markov process, we take an independent subordinator, consider this time-changed process, and we obtain again a Markov process. Of course, I do not prove anything, I just inform you that this is life. Okay? So, may I go further, or do you need some further explanations to what we have seen? Are there any questions? Okay, so this is the procedure. So again, the aim was to construct a new semigroup from the old one, a single one. So this is a nice operation, which makes sense in the analytical side, and also which has a reasonable sense in the sense of stochastic. So it's a random time change by means of independent process, which is a Levy process with non-decreasing path. So
if I was thinking the particular case where the subordinator is a Poisson process.
What?
If that subordinator is a Poisson process. Poisson process.
Poisson process. Ah, Poisson, yeah, okay, yes.
So then this will lead to some of the interesting representations like a resolvent type of things.
Yes, I guess.
Yes. maybe there will help with some computations.
Probably, but I do believe everything is already done.
Okay.
I have seen some such things in some talks. Yeah. Yeah. But still, you see, in stochastic it's an interesting procedure. We take a Markov process and we make a random time change. Instead of deterministic time t, we consider random time given by an independent process with non-decreasing path. If it is moreover a Levy process, then we again obtain a Markov process. Time change process is again a Markov process.
Can I say what's some remark again?
Yeah.
So if you change it to Poisson process,
Yes.
then it looks like that's this.
Okay. Also again jump process.
But do you change the time to that's a discrete time?
Well, yes. So we obtain then again like a jump process.
Maybe you can Markov chain type or scale it and
Something. Yeah.
Yes.
Yeah. But so if you have a psi a Brownian motion, and you use alpha like beta stable subordinator, then you obtain as a time change process you obtain two beta stable Levy process. So it should be yeah. So it was supposed to give this example, but later on when one would understand why it is so. So remark. So if my original semigroup was even Feller semigroup, that is my corresponding Markov process is even a good process, even Feller process, then the time change process, so the corresponding subordinate semigroup is also Feller. Moreover, if my TT semigroup, original semigroup corresponds to a Levy process, and say Levy process corresponds to the function psi, yeah, as yesterday, to a single psi from the Levy-Kinchin formula, then the time change process is again a Levy process, and the corresponding symbol in the Levy-Kinchin formula is just composition of f and psi, where psi corresponds to the process psi, and f corresponds to the subordinator. So let me clarify at least this statement. So you see, I try to, not to prove, but at least to persuade you that it is something reasonable. Again, what I do, it's not rigorous calculations, but just some calculations which can be made rigorous. So how acts our semigroup, our subordinate semigroup on phi? This is integral from 0 to infinity, ts phi eta t ds. So assume we have a nice phi, and this semigroup corresponds to a Levy process. So we know that for nice phi, the semigroup is given by pseudo-differential operators. That is, we have the following for the semigroup TT. It is Fourier inverse, composed with E minus T psi, composed with Fourier, phi, and then eta t ds. Yeah, psi is the symbol, so minus psi is the symbol of the generator of the semigroup, and also called the symbol of the process, corresponding to the process. So assuming we can interchange all the integrals, I can rewrite it, okay, yeah. Assuming we are able to interchange all the integrals, this is just something like this. Yes? Fourier is integration, and inverse Fourier is also integration. So I have interchanged integrals. Okay, but what is written here? It is nothing else but the Laplace transform of measure eta at point psi. But we know that the Laplace transform of eta at point psi. Oh, it does not want to go further, but it has this form. Yes? Hence, inserting it here, this guy is nothing else but e to the power minus t f composed with psi. And hence you see exactly this, that this operator is a pseudo-differential operator with this symbol. With this symbol. Now one has to prove, of course, that this composition, f composed with psi, is again a function of the type which is given by the Levi-Hinche formula. But one can show it, and after that, you see that the semigroup corresponds again to a Levi process, and this Levi process has this symbol, f composed with psi. So I try to persuade you that the last statement is true. And then probably you can guess, or you don't need to guess, you know from the previous lectures, that if the semigroup is a family of pseudo-differential operators with symbol of this type, then what would be the symbol of the generator of the semigroup? Just take a derivative with respect to t of this guy at t equal to 0. I don't hear. I don't understand what does it mean. F of psi, exactly. F composed with psi. And moreover, even in general case, even if we don't speak about the Levi process, but just about the semigroup, it turns out that the generator is again f of psi. So recall that, I don't know where to write it down. So what does it mean that the operator had a symbol, Fourier inverse composed with so minus f of no place anymore, so I have to clean it. So we have discussed that my L looks as follows. So this is a pseudo-differential operator with symbol, so minus always there, f of psi. Yeah? But psi, so we know that, so this is my L eta, the generator of my subordinate semigroup. But the generator of the original semigroup had symbol minus psi. So in a sense we have minus f of minus L. Yeah, so this is in a sense minus f of minus L. Yeah? Here we have f of psi, and psi corresponds to minus L. Okay? So actually this is true not only for the case that we have a good process, but always in discuss subordination. We have this, that the subordinate semigroup has generator, which is a function minus f of minus L, where L is the generator of the original semigroup. Now how to understand this? What does it mean, function of operator? And now what is helpful for us is that f has Levi-Hinche representation. The sigma, lambda, mu are Levi characteristics. I'm sorry. So this object is defined by this way, but this is just the Levi-Hinche formula for f, where instead of z we have inserted minus L. And instead of e to the power Sn, we inserted semigroup. So it's a kind of functional calculus which we have to do. Okay, so this is, yeah. So this is everything about subordination, and we make a break, like 5 minutes break, for you to accept all this, and then we start a new topic. But maybe there are questions. No, okay. So it is something new, I guess. So a new operation which has an analytical aspect and stochastic aspect. So we start at 10 next lecture. Walk a little bit. It's not possible to sit so much time.